Many real-life problems involve a process called optimization, in which we want to find the maximum or minimum value of some quantity. This applies oftentimes in business applications in which we want to maximize our profit or minimize our costs. In this video, we will study one type of the optimization process used currently today and in the past, which is called linear programming. Linear programming is the process of finding that optimal solution. The objective function is our goal. It's what we want to minimize or maximize, and it's written as a function. Our constraints then, in life we're always bound by certain constraints. Our constraints are going to be written as a system of inequalities. And I'm just going to write that it's based on our limitations. Sometimes those limitations can include how much of a product we have, or how many hours a worker could work. Once we graph our system of inequalities, we'll identify our feasible region. This is the solution to the system of inequalities. The vertex principle says once we graph, we identify our system of inequalities and we graph to find that feasible region, the shading, or the solution to the system of inequalities. Once we do that, the vertex principle says that the minimum, or the maximum will occur at one of the vertices, or the vertex or the corners of the feasible region. Our optimal solution is going to be based on our objective. If our goal is to minimize, we want to pick the vertex that provides us with a minimum amount of something when we plug it back into our objective function. If we want to maximize, our optimal solution would be the largest value based on a vertex. So our optimal solution is going to be the one vertex that provides the desired minimum or maximum. And it's all based on what the problem asks for. In this video, we're going to take a look at these examples, and they only cover half of the process of linear programming, but we want to really solidify this process so that when we move forward with transferring from words or applications into our system of inequalities and our constraints, that we only have one additional step to add on to the process. So within linear programming, we're going to want to create a system of inequalities. This system of inequalities represents my constraints. So in problem number 1, this whole system here, those are my constraints. Okay, my constraints are my restrictions. So for these restrictions, the first thing I want to do is graph each system of inequalities. So I want to graph all 3. In this particular case, in example 2, it'll be all 4. So I'm going to graph all 3. So feel free to pause the video and graph all 3 of these on your own. Okay? Once you do so, then check your work against my answer. So hopefully you're able to get the exact same graph with this center triangle being highlighted as your final solution for just graphing the inequality. That region in there represents, back to our vocabulary, this is the feasible region. It's all of our possible solutions. That feasible region is bound by some vertices. I have 3 corners. Those vertices are located to the right 3 and up 2, to the left 3 and up 2, and then to the right 0 and down 4. Okay, these 3 vertices, based on the vertex principle, are the only possible options for maximizing or minimizing my objective function. My objective function is given here. For my objective function, I'm told whether I want a minimum or a maximum. In this case, I want a max. So I'm trying to maximize this function. This function is c equals negative 2x plus y. My corners, or my vertices, are these 3 that I found here. So negative 3, 2, 3, 2, and 0, negative 4. I'm going to substitute the x and y value into my objective function and get a value. So negative 2 times my x of negative 3, right, plus my y value of 2, right, that's going to give me 8. So I'm going to make a note of 8. If I substitute in 3, I have negative 2 times 3 plus 2. That's going to give me negative 4. And if I substitute in 0 and negative 4, I end up with negative 4. I wanted the maximum. Right? Based on these 3 values, my maximum is clearly this top line of 8. That means that my optimal solution is negative 3, 2. So my optimal solution would be negative 3, 2. It would give me a maximum value of 8. Okay, let's reiterate this. Okay, let's summarize our steps. Okay, first thing I want to do is I want to graph. Second thing I did was to identify the feasible region and my vertices. Third, I test each vertex. And lastly, I've picked the one that's most ideal, the optimal point. And optimal depends on what I'm being asked. Here I was asked for the maximum. That was what was optimal in this situation. In this second example, I'm being asked for the minimum. So again, if you feel as though you're able to proceed and try it on your own, go ahead. If not, I'm going to go through it step by step with you. I'd like for you to graph this first. X has to be greater than or equal to 0. So if it's greater than or equal to 0, X is greater than or equal to 0. That means I need all my X values, right, that are greater than or equal to this vertical line. That's everything in the first and fourth quadrant. But then when I have Y is greater than or equal to 0, that's my horizontal axis. Right? I need everything above that. So that means now I'm limited only to my very first quadrant, and this line was off a little bit. You get the idea, right on the x-axis. Okay, so these two other inequalities are going to really restrict that. Let's do this other one first. Y is less than or equal to 6. So up at 6, I have a horizontal line at 6, and all my values are less than that. So now I've shrunk down even further. So the only thing that I even kind of have an option for right now is this region here. But I haven't even finished. I have one last inequality. This one has to be solved for y. You should all know how to do that, so I'm going to rewrite that inequality down here. It would be y is less than or equal to negative 3x plus 15. And if I graph that, I start up at 15, and I'm going to count down 3 and to the right 1, down 3 to the right 1, again down 3 to the right 1, down 3 to the right 1, and lastly down 3 to the right 1. Okay, and I'm going to graph this line, and I need all my values that are less than that. Well, all my values less than that are all this way. So final feasible region is the place that includes all of those scribbles. Well, that region is located here. It's a trapezoid. That means in this case, my next step is to identify my vertices. Okay, I want to identify each vertex. Well, I have 4. One here, 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 and here. If I write those out, my corners are at 0, 0. I have another one to the right 0 and up 6. I have a third one to the right 5 and up 0. And my last one is to the right 3 and up 6. I want to test all of these in this function. So instead of writing out all my steps, I'm going to do this in my head. 3 times 0 plus 0 is going to give me 0. 3 times 0 plus 6 is going to give me 6. 3 times 5 plus 0 is 15. And 3 times 3 is 9 plus 6 is 15 as well. Okay? Now I wanted the minimum, right? The minimum amount. So in this case, the minimum amount is 0. So if I want my minimum amount is the ordered pair 0, 0. It gives me a minimum of 0, and therefore this value here does indeed give me my min. Again, in summary, vocabulary. These are my objective functions that I'm trying to minimize or maximize. I do that by graphing my constraints or my inequalities to identify a feasible region, and then picking my vertices, my corners, because my vertex principle tells me that the minimum or maximum will always occur at a corner.